Need for Speed Heat is the latest installment in EA's racing game franchise running on the Frostbite engine. The gameplay is centered around the daytime and nighttime high-speed races with exotic sports cars in a large open world. In this talk, we're excited to show some of the rendering techniques used to achieve high-quality visuals at fast streaming speeds in an open world.
Hello, my name is Andreas Lindqvist and I'm a rendering engineer at EA Gothenburg. I will talk about how we used reflections in Need for Speed Heat.
My name is Kleber Garcia. I am a rendering engineer in the Frostbite team, and I will be giving an overview of global illumination.
Hi, I'm Andreas Brink. I'm a rendering engineer at DICE LA. I'm going to start this presentation by talking about some of the improvements we made to the material system in the latest Need for Speed. Frostbite started its transition to physically based rendering in the fall of 2013. Like many other game developers, we adopted a simplified version of the material parameterization introduced in the 2012 paper Physically Based Shading at Disney by Brent Burley. In the terminology of that paper, we used the base color, metallic, specular, roughness, and clear coat parameters. Frostbite primarily uses deferred shading, and we store these parameters together with a few additional ones necessitated by the deferred approach in a 128-bit G-buffer. This is a conceptual view. For instance, we store smoothness rather than roughness, and specular is really index of refraction. 2 years later, we shipped the first Need for Speed using the new parameterization. From a rendering perspective, the game was pretty successful, and we were even able to convincingly composite real-world footage with computer-generated imagery in real time. We used the same parameterization in Need for Speed Payback in 2017. But when we started working on what was to become Need for Speed Heat, we decided we wanted to improve our material model. We wanted to be able to better represent a number of materials which had been problematic in previous games. The first material we wanted to improve on was lacquered carbon fiber. Carbon fiber weave has a clearly visible macroscopic structure. When the weave is covered in a coat of smooth varnish, the specular lobe should use the normal of the coat and the diffuse lobe the normal of the weave. In our previous games, we tried to fake this by modifying the base color and roughness of the material. The second material which was giving us problems was matte clear coat. Most cars use a smooth coat of polyurethane, but some, in particular high-end cars, have a non-smooth finish on the coat. For non-metallic paint, this could be represented through the roughness parameter, but for the case of metallic paint, this was not possible. Metallic paint consists of a colored binder with metallic flakes in it. The flakes give rise to a second specular lobe in addition to the one from the clear coat. These two lobes are loosely coupled and were not possible to represent in our original parameterization. As an alternative to the metallic flakes, there are also several types of mineral flakes which change color depending on the incident angle. The final type of material we wanted to tackle was free-stage paint jobs. In a free-stage paint job, a middle translucent stage is added on top of the base coat before the clear coat is applied. The second layer fills out some of the light reaching and being reflected off the base layer. This layer can also have flakes of various types added. The effect is one where the color of the diffuse and specular lobes are decoupled and can also vary with view angle. To support these materials, we needed to add a separate normal for the coat, a separate roughness value for the coat, and a separate specular color independent of the base color. In addition to the deferred renderer, Frostbite also has a fully featured forward renderer. The first thing we tried was rendering the base coat in the deferred pass and the second stage and clear coat in a transparent forward pass. This worked reasonably well from a quality perspective, but was more expensive than we could afford. The performance problem was threefold. First, it will nearly double the number of draw calls for the cars. This was already becoming a problem due to the large amount of customization we were adding to the game. Second, it would double the amount of vertex processing on the GPU. Third, Rendering the forward layer was very costly since it combines all lighting and material calculations into one shader. These shaders had a very high GPU register usage, which meant poor occupancy and in turn poor performance. We came to the conclusion that the forward method wouldn't work and that we would have to add the required parameters to our deferred rendering model instead. We opted to add an additional 64-bit channel to the G-buffer, which would be selectively written depending on the material in question. We obviously didn't want to add the cost of reading the extra parameters and the more complex lighting model to the regular materials, so we needed a mechanism to separate the lighting of these two different categories. The tile-based deferred renderer in Frostbite already categorized tiles into two tiers based on whether they included either subsurface scattering or simple clear coat materials, or standard materials only. We considered 3 different alternatives for how to extend this categorization. First, we could generate separate shader permutations for all combinations of materials. Second, we could dispatch each tile once for every material it contained and mask out pixels of the wrong material. Third, we could do a direct extension of the existing method and add a third tier which could handle both the new materials and the 3 existing ones. The first alternative was discarded on the drawing board. We wanted whatever solution we choose to be possible to extend with additional material models in the future. Having a separate shader permutation for each combination of materials would make the number of shaders grow exponentially with the number of materials. The number of shaders were already becoming a problem, so we decided that this was not a viable option for us. The second alternative was the first one we tried. Even though this approach turns all memory accesses of the masked out threads into no-ops, the number of dispatch waves was doubled for tiles with both the existing and new materials. Also, just the code necessary for the masking added a small but measurable cost to all tiles. We didn't immediately discard this alternative, but decided to try out the third option as well. With the third alternative, the cost of tiles with only the new material is increased slightly compared to in the second alternative, since the shader still needs to handle the existing materials. The cost of tiles containing both the new and existing materials was decreased though. In the end, whether the second or third alternative was faster depended on the ratio between the number of tiles with the new material only to the number of tiles with both new and existing materials. In our worst case scenario, we had quite a few cars of varying sizes on screen, which meant a lot of bordered tiles. Here, the third alternative was 0.1 to 0.2 milliseconds slower on the base Xbox One, which led us to go with alternative 3. Here is a short video of the new materials. Once we had a framework for the new materials up and running, we realized we could use it for more things. The first use case we found was hair rendering. Up to this point, the most sophisticated hair in Frostbite had been done by rendering the opaque core of the hair strands in a forward-rendered opaque pass, and then adding a forward-rendered transparent fringe to soften the look of the strands. The model used was a modified version of the one introduced in A Practical and Controllable Hair and Fur Model for Production Path Tracing by Chang et al. With the new framework, we could replace the opaque pass with a deferred pass using a new fourth tier of materials. This reduced the cost of our hair rendering dramatically. In this close-up of the character Anna, the opaque part of the hair was originally sitting at 11 milliseconds on the Xbox One. Making the switch to deferred rendering added 1.2 milliseconds to the G-buffer pass and 1.6 milliseconds to the lighting pass, but it also removed the 11 milliseconds from the opaque pass, so in total saved us more than 8 milliseconds. Together with a few other optimizations, this was enough to let us play back most of our cinematics in real time, which let us put the customized player avatar and car in them. It also made it easier for us to support different display aspect ratios on the PC. Anna's hair has a huge amount of overdraw, which really puts this system to the test. The second use case we found was retroreflectors. In previous games, these had been faked by our artists. This was done by adding emissive light from retroreflective surfaces based on the position and orientation of the camera relative to the surface. This worked reasonably well under normal gameplay when the camera was situated roughly at the same position as the car, but broke down when switching to a third-person view. There was also a cost associated with rendering the emissive light, since that's a separate pass in Frostbite and not part of the G-buffer. We created a new material model for the retroreflectors and moved them to the deferred pass. There are two main categories of retroreflectors: corner and spherical. Corner reflectors are made up of hexagonally tiled corners and typically used on road signs. Spherical reflectors are made up of tiny glass beads with a carefully selected index of refraction and typically used on road line coating. To simulate this, we added a model with a separate specular lobe from a microfacet distribution oriented towards each light in question. In the factor adjusting for the light incident angle, the surface normal is still used though. Retroreflectors are usually covered in a colored transparent layer, which filters the response. This also means we still get a normal specular response from the outer interface of the material. Similar to how we handle metals, our artists could also specify which fraction of a surface should be covered with retroreflectors. We use this value to blend between the standard material and the retroreflective material. Finally, here's a short clip of some of the retroreflectors rendered in-game. I'm now going to hand over to Kleber, who will talk about our global illumination.
Need for Speed Heat is a game that supports multiple times of day and weather conditions. We chose to have a full-baked lighting data to maximize image quality. Time of the transitions are discrete, and there is no blending between them. This creates an opportunity to maximize on quality and performance. Need for Speed Heat is considered an open world game. This means that a lot of the artist's workflows must be automated in order to scale on a large map. This is where things get tricky with Frostbite's previous global illumination solution. The previous solution consisted of light maps and manually placed probe volumes. The probe volumes are manually placed by the artist in our editor, and an artist has to assign dimensionality for each volume. This has many limitations in terms of quality and performance. In terms of quality, models used to contain a single interpolation point, which is computed in the CPU and can incur in performance penalties the more meshes that request probe lighting. In terms of scale, the manual placement can be often time-consuming and also very difficult to tune for memory and performance. We developed an automatically placed sparse GPU probe grid, which scales to large worlds. Our GI grid supports automatic probe placement, multi-resolution interpolation, artist-driven density assignment, and per pixel interpolation using hardware filtering for improved radiosity fidelity. I will first cover the auto placement algorithm, followed by GPU resource packing, and finally with some runtime details. The auto placement process starts by an artist either automatically assigning densities, dropping hinting volumes, or simply batch tagging geometry. For example, roads maintain a higher probe density so the car's radiosity can catch the detail bounce from streetlights. Once this process is done, an artist can choose to do placement on the entire world or on a particular zone of the world. When the auto bake button is pressed, we kick off our path tracer, Flux, which bakes and automatically places probes on the scene constructed. The algorithm picks up geometry from the scene and subdivides the world into equally sized cells. A cell is a cube with unique distance assigned by an artist in the probe grid asset prior to auto baking. The cell is our streaming primitive, meaning that we stream level of details depending on distance or pixel coverage. What is interesting about our cells is what's inside of them. Inside, we encounter a sparse irradiance tree. Each node consists of a 3x3x3 spatially divided cube, with probes in the corners and recursively containing child nodes within each subdivision. We generate this tree by first working on a cell individually. We aid the placement process by first generating a distance field. Our implementation uses an algorithm called distance transforms of sample functions. To generate this distance field, we first transform the geometry in the cell to a dense point cloud representation voxel grid. We run the distance transform algorithm and store it into a volume of floating point numbers. Each number represents the distance to the shortest geometry in the domain. We take all the bounding boxes of the objects in the scene and store them in a bounding volume hierarchy, or BVH, for accelerated spatial querying. We also construct a BVH for the scene triangles and use CPU ray tracing to aid our placement algorithm. We decided to use a 3x3x3 split topology for each node in the irradiance tree, since it was a good balance between probe density and streaming memory. Starting at the root, we first test each subdivision of the current level against the distance field and check if there is a geometry close by or not. Once we assess that there is a geometry in the partition space, we proceed to place probes in the corners. The bounding boxes of the geometries inside the subspaces are queried for density tests and assess whether we can continue our subdivision process or not. We continue with this process recursively until we reach the maximum level specified by the artist. After placing a set of probes in a level, we then do a more granular ray tracing test on the placed probes to assess if there is a significant geometry around. This test will let us call some of the probes that are far away from geometry. Notice how the probe node primitive has a fourth row of probes in all its axes. These are shared probes between the neighbors on the same level. So when we do our baking process, we only bake that location once. We group complete sets of the tree levels by memory size and treat each of these sets as streamable blobs, which then get stored into a cell. For the sake of explanation, we're just going to pack a single level at a time. In this example, we can appreciate the level getting split into a set of bricks of size 8 by 8 by 8. More dense levels will have more bricks. The bricks can have empty waste in them, but by being similar in size, it simplifies runtime dynamic allocation for a volume atlas. In this 3D representation, the corners of yellow cubes represent probe coefficient data. The blue cubes represent our bricks. We can see how each cube corresponds to a logical location into a brick pool for that particular streaming blob. Notice that there will be some duplication in the edge of these bricks to allow spatially continuous interpolation. The brick layout allows us to dynamically allocate memory at runtime without having fragmentation. The memory is allocated by treating a volume texture as a pool of equally sized bricks. As the car progresses into the world, we dynamically stream in and stream out blobs containing bricks into this volume atlas. In the GPU, our tree is represented as a flat list of nodes. A node has two bit masks, one for its active children and another one for the active probes in its corners. A node has also two offsets, one that points to the dynamic brick addresses and another one that points to its tightly packed children in the same list. Because the children of the same node are tightly packed in a tree, we can count the bits from the child's nose mask to jump to the desired child. The same situation applies with the dynamic set of addresses. The addresses are patched at runtime in compute depending on the streaming requests coming in from the car's position. Each cell can be sent to its own baking agent, making the placement a perfectly distributed problem. Once agents in our baking farm finish the irradiance tree placement, we gather all the probe positions as an individual list. These positions can be split into equal work batches and distributed to our baking farm once more for irradiance generation. Flux will then compute irradiance by shooting paths on each probe and storing this information in the logical brick chunks. One problem we face is the seams between transition of levels. Notice here, for example, in this scene, we have a transition from higher density to lower density. This transition is harsh because there's a difference in resolution at the boundary. Remember the probe tree? After placement, we post-process the tree and we look for probe islands by running a flood fill algorithm. A probe island is a group of probes that have no empty space or child probes between them. Once we identify these, we choose to code them with virtual probes. We define virtual probes as interpolation caches of the parent nodes. If we do this, interpolation then becomes smooth as long as we are in the same cell. This solution does impact the amount of probe memory used, but it was a good compromise to keep sampling cheap and the runtime simpler. One last issue remains, and it is blending between two adjacent cells. Regardless, even if we duplicate the same shared probe wall between these cells, we can still end up in a situation where one cell is streamed at a higher LOD than its neighbor. This will, of course, cause a seam due to the discrepancy in resolution. There are many ways to fix this, such as tweaking the lighting, pre-computing some light factors, but what's not attractive about this solution is that it has to be done at bake time and is computationally expensive. We would like a solution that can let us independently define how we bake irradiance for these probes. The most naive way is to sample the grid 8 times. Basically, walk the grid on each corner and then do interpolation in the shader. Walking the tree hierarchy 8 times per pixel is not something cheap, so we are now stuck, unless we can somehow do this stochastically. Our first step is to translate the problem from world position to camera position. Because the hierarchy can be walked per pixel, we can create some sort of cascades or limits into level of the hierarchy. This exchanges the harsh cell shape artifacts with a more consistent camera cascade artifact. We can think of these clamps in the hierarchy level as probabilities. The more this area gets closer to the next, the higher the probability that we will jump to the next level in the hierarchy. If we do a simple comparison with some screen space blue noise, we will be able to hide the artifact even further and rely on our post-processing denoiser effects to hide such artifact. We did not choose to vary the noise temporarily to avoid creating unstable artifacts. A simple blue noise texture sample spatially in screen space is enough to hide the seams. There are a few artifacts that occur when we have a grid structure to represent GI. One of them is stair-stepping in curved surfaces. The same artifact causes a clear difference in color on multi-resolution areas. These artifacts occur because the probe positions are placed in a grid, and some probes end up seeing back faces. A naive solution is to paint these back faces black, but this can cause this sort of discoloration. After auto placement, but before baking, we decided to take those probes that see back faces and shoot some rays around them using a low discrepancy distribution. For each ray, we apply a sandwich algorithm where we shoot an opposite ray coming from the neighborhood's radius. The neighborhood distance around the probe corresponds to the distance to the closest probe in the grid. This will make the probe find the closest most valid surface position and teleport it to this position for bake time. Because the position the probe can be teleported to is constrained, this doesn't cause the GI to be too biased. We still use the grid position for sampling. The results are smooth surface irradiance and quite good resistance to tricky geometry with back faces. We now have a GI system that can interpolate, stream in, and scale on an open world. Frostbite's GI has been traditionally applied through our G-buffer laydown pass into an irradiance G-buffer. We call this our object lighting G-buffer. An advantage of this is that it allows sky visibility and indirect lighting to be read and written in the shader graph. Behind the scenes, our old probe system would apply probes by setting the coefficients through a constant buffer in the CPU for each instance. This, of course, is what causes large meshes that sample probes to be disconnected from the environment and light map lighting. Now that we have an irradiance tree, we have fixed this problem, but walking a tree hierarchy is something that increases costs during G-buffer laydown. The complexity, loops, and conditionals can certainly increase register usage on an already expensive pass. To make matters worse, geometry that does this heavy overdraw can also suffer from this performance penalty. Some typical approaches to avoid this cost is to cache the tree hierarchy in some sort of cascades clip maps. Because we wanted to preserve our irradiance tree's sparse quality, we did not create a clip map cache. We decided to go with a different approach. Not all of the objects in the scene require reading sky visibility or hijacking indirect lighting. Thus, in the pipeline, we can parse our shader graphs and make a decision whether GI gets applied during G-buffer laydown or in a deferred pass. We provided tools as well to the content creators to identify expensive and cheap shaders this way. As a result, we were able to maintain our GPU performance and avoid excessive register usage on materials. In our defer pass, meshes that have no GI dependency on the shader graphs will write a stencil bit indicating whether they require probe lighting or not. In this deferred GI pass, we then use the stencil and apply GI from the probe grid this way, avoiding overdraw costs. Forward passes, such as our reflection pass or transparent materials, still must run the hierarchy in a non-deferred fashion. But this was an acceptable performance cost increase, since we have now saved all the CPU work from the old probe system. Our particles and participating media passes benefit from the GPU representation, since they can now sample irradiance per pixel, as well as volumetrically. This increases the fidelity and richness of many scenes. In the case of participating media, we only have to sample the first band of our spherical harmonics to treat it as volumetric average lighting. Frostbite provides us at the file system level with traditional zlib compression. Once this data is streamed from disk and decompressed, there are other layers of compression that we could apply to our probe data. Without compression and using two bands, each probe could have a total cost of 512 bits. We could reduce the precision of each probe to 16 bits, which can give us an improvement for a total cost of 256 bits. We could try going to 10 bits representation, but unfortunately this would cause a lot of HDR precision problems. On the other hand, we can treat the SH in another color space. We can extract the total luminance and chrominance of the entire sphere and pack it in 32 bits. We can then use 3 more components for a second band as a chrominance color space. This will give us a grand total of 128 bits. This is also called log LUV compression. Our global illumination grid can also support runtime updates. It is integrated with our GI Live Preview system, which utilizes DX12 RTX to calculate irradiance. It allows artists to change lighting and move geometry and preview global illumination changes without having to wait for long bake times. More information on our GPU path tracer can be found in our talk, Interactive Light Map and Irradiance Volume Preview in Frostbite. Because lighting is dynamic, we have to patch virtual probes in the GPU and can't pre-compute them. We patch them very efficiently by having a compute shader that resamples the grid and scatter writes irradiance into the brick pool. A problem with irradiance volumes is light leaking. The light leaking occurs due to the discretization of the irradiance through the grid, which does not represent the highly nonlinear nature of the actual irradiance field of the scene. We have solved this problem by providing a manually placed GPU probe volumes with blending factors and free transform that leverage our volume atlas technique. In this example, we can cover up some problematic area without having to increase resolution on the entire grid. Usually, indoor scenes tend to be problematic, and thankfully they don't account for the majority of the world in a racing game. I will now hand it to my colleague, Andreas Lindqvist, who will talk about reflections.
Reflections are important for a game like Need for Speed Heat, where a large open world and strict streaming constraints limits what can be achieved in content. Reflections can help make the game more interesting and add welcome detail. Frostbite supports 4 different reflection types, all of which were used in Heat, and I'll begin by giving a brief introduction to them. Stochastic screen space reflections is Frostbite's screen space reflection implementation. Based on the surface normal and the G-buffer material properties, a small number of rays are traced for each pixel. Like in ray tracing, the reflection vectors are chosen based on BRDF importance sampling. Screen space ray marching is then performed along the reflection vectors until a hit is found and the color buffer is sampled. The hierarchical depth buffer is used as an acceleration structure to improve the ray marching performance. To increase the number of samples, ray results are shared between neighboring pixels, and a temporal filter is applied by reprojecting the result from the previous frame. Rays are set to fade out when there is insufficient screen space information available. Planar reflections capture the scene as seen through a mirror plane. They are most accurate for flat surfaces with mirror-like materials, though the Frostbite implementation can handle variations in the surface roughness and the normals in a robust way. Environment maps in the form of cube maps exist in two different forms in Frostbite: dynamic reflection volumes, which are continuously updated, and static reflection volumes, which can be either pre-rendered or initialized once they have been loaded. Reflections are composited in the following priority order: first SSR, then planar reflections, dynamic cube maps, and finally static cube maps. Need for Speed 2015 used static cube maps for all reflections. The reflection volumes were manually placed by lighting artists and updated as they were streamed in. The cost of updating a volume was amortized over 7 frames, 6 for the cube map phases and 1 for the convolution step. This solution held up quite well, partly because the game had a soft filmic look and took place exclusively at night. Need for Speed Payback, which was released 2 years later, also relied on static cube maps for its reflections. The hardest constraint that we faced in Need for Speed Heat was streaming performance. It's possible to drive 400 km per hour in the game, and at that speed, world assets are streamed at the rate of up to 30 megabytes per second to keep up with the player. That does not include the streaming of terrain, audio, AI, and patch data, or the free streaming of detailed LODs and MIPS. The disk read performance may be as low as 50 megabytes per second, depending on where on the disk the data is located. All in all, this meant that we had to rule out solutions which depended on streaming reflection data from disk during gameplay. For Need for Speed Heat, we wanted to combine the strengths of Frostbite's different reflection types. The techniques all have different advantages and disadvantages. SSR, for instance, provides high-quality reflections under the right circumstances, but can also introduce severe artifacts where screen space information is missing. A dynamic environment map captured at the player location is a good approximation for the car, but does not project well onto a building in the distance, etc. Here we face two problems. First, there was no way to restrict how the different techniques were applied. All techniques were applied to all objects. And secondly, we weren't sure how far we would be able to take the idea for performance reasons. We added a setting on our materials containing a mask of which techniques should contribute to the reflections. Fortunately, we were able to optimize the G buffer and free up 2 bits in which we stored the mask. One thing that we felt had been lacking in the previous 2 games were the car reflections. The player car can be seen in full detail in the garage, some of the menus, and in the photo mode. So for Heat, we decided to add the dynamic cube map and use it primarily for the player car. For performance reasons, the dynamic nmap is forward rendered and only captures sky and sun lighting. We rendered most world objects, including buildings, trees, roads, and terrain, into the cube map, but not other cars. The fact that the cube map was forward rendered also meant that we could add multi-sampling to it. We enabled 4x multi-sampling in the garage and in the menus, where we had the required memory and performance to spare. The nmap resolution varies depending on platform and user settings, from as low as 128 by 128 up to 512 by 512. The reflections in the wet roads are important to depict the heavy rains that takes place in the fictional Miami where the game is set. Here we rely mainly on screen space reflections, but we also render a planar reflection which is used as a fallback solution. The planar reflection is applied where SSR fades out because of missing information, and for the part of the road with a roughness value over a certain threshold, where the result from SSR would either be too noisy or require too many rays to be performant. The planar reflection is rendered at 40% of the resolution of the main view. To determine the orientation of the planar reflection, we perform a set of ray casts against the collision geometries. The rays are arranged in a grid pattern in a small area around the car. The intersection points and normals can then be used to approximate the reflection plane. But how should we calculate this plane? The first option we tried was to use the least squares method. Unfortunately, this only worked well when we actually wanted all the points to be part of the solution. If one of the rays hit an object or another car, that would cause noticeable changes to the reflections. Instead, we successively apply a cross-shaped median filter to the angle formed between the intersection normal and that of its neighbors. After this, we apply a low-pass filter to temporarily filter the resulting normal. Finally, we choose the median plane from the planes formed by this normal and the original sample points. This solution robustly handles curves and the case where some rays miss the road entirely. The solution with static cube maps that was used in the previous two games would have worked well for buildings and other world objects. However, we could not afford rendering even a single side per frame of a deferred rendered cube map. Instead, we used a set of 8 pre-rendered cube maps for each time of day to provide ambient reflections for most of the world geometry. The volumes were spread out over the world, one for each distinct area of the map, and were kept resident in memory. They were stored as BC6HU textures, i.e. without delta. The compressed size of each of the 3072 by 512 textures was about 1.5 megabytes. For the water reflections, we relied exclusively on SSR. One option we discussed but had to rule out for performance reasons was to use a planar reflection for the water as well. In some parts of the world, city skyscrapers can be seen reflecting in the water from a long distance. This caused precision problems for SSR, where the rays start and end points were stored as UV coordinates in an FP16 buffer. UVs are between 0 and 1, and FP16 has limited resolution in this range. Fortunately, we could improve reflection precision by moving to a 16-bit UNOM format instead. This is a visualization of the reflection masks. Here we can see that almost all objects can receive reflections from static cube maps. Next is the mask for the dynamic cube map. And finally the mask for planar reflections in SSR, which in our case is identical. Let's look at the breakdown of how the different systems are used together. Here's an example of a night scene with only sky reflections. Then the set of static cube maps is added, followed by the dynamic cube map for the player car, then a planar reflection, and finally screen space reflections. Here's a similar scene but at daytime. First with only the sky environment map, then the static cube maps, the dynamic cube map, planar reflections, and finally screen space reflections. One part of the solution to the performance problem was to have the cheapest possible LODs for the reflection use. To achieve this, we built a tool to project a detailed LOD onto a simpler imposter geometry with an unwrapped UV set and a single material. This also meant that we could reduce the number of draw calls by merging objects with the same material into larger meshes. Reducing the number of draw calls was particularly important on the PC version of the game, which used DX11 and was often CPU bound. Consider the city buildings, for example. These used a definition that captured the G-buffer base color into the RGB components and the roughness into the alpha component of a BC7 compressed texture. If the object had one or more emissive materials, the emissive color would additionally be captured into a high dynamic range BC6HU texture. And if it was metallic, this information would be stored in an additional BC4 texture. One thing that we wanted to address in an update was the shadowing artifacts that often plague SSR. This happens when a ray should trace behind an object in the depth buffer that is killed prematurely because there is no information of how far the foreground object extends. We dubbed it the poncho effect because of how these artifacts typically look. It's possible to work around the issues by using techniques like depth peeling or deep G-buffers. We added late G-buffer pass and a second layer to the hierarchical C-buffer Some objects, like the cars, are tagged as foreground objects and rendered into late pass. If we detect that a ray passes behind one of the foreground objects, the ray is deferred to a second SSR pass.
Thank you for your time, and to everybody who contributed directly and indirectly into this project. We hope to see you next time.